Okay, so we're going to be proving today one of the integral formulae that you will need to know for calculus. It's quite useful. You might see it sometimes. And if you see this integral and you don't know the formula, it will be pretty hard to arrive at this same result. So in order to prove this, I'm going to be differentiating arccosine of x and hopefully arriving at this result here. So let's begin. We'll let y equal to the arccosine of x. So the cosine of y is equal to x. And let's bear in mind here, x is the cosine of y, which means that -1, x is bounded by essentially -1 and 1, and y is bounded by pi over 2 and -pi over 2 because of the arccosine function's range. Let's bear this in mind. Implicitly differentiate this function, we get that the negative sine of y times dy by dx is equal to 1, which implies that dy by dx equals -1 over the sine of y. Now, where do we go from here? We could substitute arccosine of x in here, although that wouldn't yield us this final result. So we need to remember this trig identity. Sine squared of x plus cosine squared of x equals 1. Sine squared x is equal to 1 minus the cosine squared of x. Now, if we take the square root of both sides, we're really only looking at the absolute value of sine x. For our purposes, it's fine. In general, it's not usually fine. But we can, for now, look at sine of x as the square root of 1 minus the cosine squared of x. Let's substitute this in here. So we get that dy by dx is equal to -1 over the square root of 1 minus cosine y squared. What is the cosine of y? Well, the cosine of y is just the cosine of the arccosine of x. Therefore this right here is simply x, because cosine y is equal to the cosine of the arccosine of x. So finally we get that dy by dx is equal to -1 divided by the square root of 1 minus x squared, which is the thing we're trying to prove. I hope this helped. It's certainly not easy proving this, but once you know the basics of implicit differentiation, you know some trig identities, it's really not too bad. But I hope this was informative. I hope this inspires you to prove the other arccosine formulae, the arc trig function, I mean the inverse trig derivatives.